Today I'll be talking about data for TensorFlow, right? So this is, we've looked at, the Weka program. We've looked at traditional machine learning methods, right, with KNN and decision trees, naive Bayes, and those were, tools that we looked at that are very popular, but they have some limitations in the fact that they don't really support big data applications. All right, so now we're going to switch gears to applications and algorithms that do support big data. So when I talk about big data, I'm not talking about 70,000 by 1,000 records. We are talking about 10 million by 10,000 or even more than that, right? So really, really large data sets. And for that, there are several approaches that we can take, including something like that is called, and I'll write it over here. So for instance, there's several solutions. One of them is something called Hadoop, right? And so that's one alternative. This is a CPU-based application. So we have Hadoop there, right? Also similar to this one, there's a framework called Spark, all right? And Spark is also, you think of it mainly as a CPU type of environment. Spark can be used with Hadoop, but it's a way of doing parallel. So all of these fall under the topic of parallel. Oops, how do you spell parallel? Right, so parallel alternatives, right? And now these are some of the ones that are available, widely known, but they have disadvantages. For instance, here you have to build clusters of computers. So basically, all the computers that we have in this lab, which are CPU-based, would have to be connected. And so you can imagine it's a lot of energy. Also, it's a headache for a system administrator to manage. A better approach, and the one that we're going to take in this class, is to use GPU-based solutions. All right, so we're going to do GPU. All right, this can be done with NVIDIA graphics cards, so NVIDIA graphics, right? And we don't need clusters, right? In fact, we're just going to be using one computer. Now, the lab here, there are several alternatives that we can take. So one of them would be to use our virtual machines. And for those of you that want to continue learning on their own, this is probably the best solution, using VMware. You can have your environment there. And basically, in that environment, you're still using CPU, but you can basically run the application code that would run on a GPU machine. A second alternative is to have an actual physical machine, so have physical machine, okay? And then the third one is to use AWS, so some kind of virtualized environment. So for our purposes, we will take these two. For the physical machine, we will use CPUs, but then for the virtualized, we will be able to log in to GPU machines. All right, so does this make sense? Are there any questions? Make sense? Yeah. All right, so these are the different approaches for parallel computing, and as I said, we will focus mainly on this one, right? How we would do things on a GPU environment. Now, the great thing about this is that the code that we need, so let's say that we're going to write some code for machine learning. That code can work both in a CPU and a GPU without having to do much, without having to change anything, really. We're going to make very few changes. And so that's the great advantage, is that you can basically learn how everything works just using a CPU, but then once you get a GPU, you can run the same code on the GPU, all right? And just assume that you have, the difference here is that you wouldn't be able to run all your data in this environment, but you can certainly run all your data in this environment. So whereas this is gigabytes, let's say, this is terabytes, for instance, right? So that's the advantage. So hopefully that makes sense, that we are not using Hadoop or Spark here. We're focusing more on GPU, NVIDIA. The code that we are using is TensorFlow. And that's something new that we're going to learn because TensorFlow is a framework that it's a different style of programming. It's a different style of programming. So we will use that, and then just be aware that TensorFlow can be used equally in the CPU or a GPU. So anyway, so that's kind of an overall picture of how the options that we have in parallel computing, and we are certainly taking this approach because of the advantages of it. All right, as I said, you don't need the GPU right away. You can prototype all your code and with a little bit of data on the CPU, same code with TensorFlow, and then once you're ready, you can either have a physical GPU or, which we do have some, right? We have some servers here on the university that we will SSH to or TeamViewer to. And we can also have some instances in the cloud in AWS. To access these, we will use a tool called SSH. All right? So anyway, so that's kind of the transition that we're making. All right? So this is why we need TensorFlow. All right? So data issues with for TensorFlow and big data. So to most practitioners, data collection is the most important issue in machine learning, and hopefully that's something that's becoming clear throughout the class. Machine learning, there's two main components really: the algorithms and the data. So you can see that. And the algorithms hardly ever change, right? So the algorithms, you choose one or the other. You really just have to learn how to use them once, and then you can always reuse them. You change parameters or the architecture, but not much has changed, whereas the data is critical, right? And that's where you spend, a lot of your time. You do a lot of your work in dealing with the data. So what are some tasks that you have to do with the data? Well, the data, you need to get the data, obviously. So you need to get the data, right? Download it from some source. Now, for this course, we'll have a lot of data sets already available, but we need to discuss a little bit of how you can create your own data as well. Then once you have the data, there's a basic pipeline. The next step is to clean the data, right? So that means, cleaning the data. Like let's say you download websites or information, and they have hexadecimal values, right? So they have, things that look like that, or 0A, hex values. So you don't really want those values in there. You want to, they're not very useful to you as they are. You really just want the ASCII characters for the language. So you want to write some code that basically replaces this with nothing, for instance, right? So in Python, that's usually like, let's say, your string. If you think about it, you'll have a string 1 dot replace, and you replace that character, or you use a regular expression, right? And you replace this with basically nothing. And that's kind of the code that you use, and that's what I mean by cleaning, right? So taking that approach. All right, then pre-processing the data. This may have something to do with formatting the data. So files need to be in a specific format for machine learning. So we talked about the Iris data set, right? So Iris consists of 3 classes, 0, 1, 2, and then we have 4 features, F1, F2, F3, F4. Oops, sorry. F4. So that means if we have a class, the class is 0, 0, 1, 1, 2, and then these are the values, right? 3, 5, 7, 7, 4, 5, 2, 1, and so on. So pre-processing means that this needs to be formatted in a specific way. So this probably translates into a comma-separated file. And the next row is 0, 3, 5, 7, 7, and so on. right? So that's what I mean by, or what we mean by pre-processing the data. So putting it in some kind of nice format. Then after that, another issue might be especially when you're using something called supervised learning. Supervised means that we have annotated data, right? So we have, like this one, this is supervised. This data set has the vectors, the feature vectors, and the classes. So we know that, let's say this is setosa, this is virginica, and so whenever a plant has these characteristics, it is setosa. All right, and so building the corpus basically means collecting the data and then having these. If this was not annotated or unsupervised, it basically means that we have no class. There is no concept of a class, and all we have is that. Does that make sense? Yeah? All right, so that's, building a corpus, and then the last part is performing inter-annotator agreement. So inter-annotator agreement relates to when, so now let's look at this example. We have two classes because it was annotated by two people. So there was agreement here. They both said this is setosa. They both said this is virginica, but for the next record, one said it was setosa, one said it was virginica. Do you see that? So this tells us that there's agreement here, and disagreement there. And that's what inter-annotator agreement means. Because this provides a specification of how subjective the features are. So for instance, if the majority of the samples have agreement, what does that mean? It's two people, two humans, read the same thing or analyze the same thing and agree. It's setosa or virginica. It's pretty easy for the humans to discover it. But if there's a lot of disagreement, it means that even two humans can't tell the difference. So how do you expect a computer algorithm to do well on this task, right? And so that's what inter-annotator agreement is, and most data sets have this. Okay? All right, so good. So data sets, data can be obtained from the web, such as text data from Twitter, for instance. So we can go, as everyone should know, data mining is about analyzing data, and there's different kinds of data sets that you can look at. Now, for this course, obviously, the focus is cybersecurity data sets. So we're talking about network data, information in the payload header or TCP header or IP headers. But anyway, data can be obtained from the web, such as text from Twitter or web pages. Specific data sets can also be obtained from machine learning libraries. For instance, sklearn, which is one of the tools we will use, has the data sets module, which includes pretty standard data sets that we will use here, like Iris and MNIST. So the names are Iris and MNIST, which are very classic data sets for machine learning. This dataset module can be used to obtain certain data sets, such as, as I said, the Iris dataset. So now let's talk a little bit, since this is, the best way to understand things is to look at code, right? So this is using Python and the Tensorflow and sklearn libraries. So the first thing is, how do we get data? So as you can see in this Python code, we use the datasets module, and we tell it to load Iris. Now, usually when this is created, Iris will contain a matrix. Right? So it'll have a matrix of data. Now, the matrix has index I and index j, all right? And those are the things we need to we can use those to extract the data, to slice it out. So let's say, for instance, if you notice here, the data sets actually divide the data into various things. So for instance, we have an iris.target, which basically represents the class, right? So the class that might be here, 0, 0, 1, 1, 0. All right, and then here, this will contain the features F1, F2, F3, F4. All All right, so if we want to separate out the data from this class, we take the iris.data matrix, and then we do something called slicing. So if you notice, this is actually looking at this that way. So we have the I and the J components, right? So we can set those up. So hereby, if you notice, there's one comma. So if we reconstruct this, we have colon, comma, and then we have a square bracket with numbers. All right, so what we're saying here with this slicing is the colon indicates all rows. So that term indicates all. So basically it means we want to slice all the rows, every single one, this one, this one, this one, this one, this one, all of them. And then we select which columns we want. So in this case, assuming this starts at 0, we're saying we only want 1, 2, and 3. And we're going to ignore 1. So that's why you say 1, 2, 3. So that means that in essence, we are going to slice out this one, and this one, but we ignore that one because this would be 0, this would be 1, this would be 2, this would be 3. Is this clear? Are there any questions? All right, so anyway, so that's one way, that's the main way that you do things in machine learning, right? In any kind of machine learning, to extract the data, you do something called slicing. All right? And there's various ways. Not every data set is going to be called iris. You know, some data sets will just be some basic matrix that's going to contain the columns and everything. But ultimately, the mechanism, the most important part here is that you can use something like that to extract your information. So this is a data set, the iris data set, for instance, in CSV format. So CSV, it stands for comma separated. It can also be tab separated. So you have the tab symbol, which is, I think, like that, right? That's the tab symbol. All right, and here you have, if you look, your columns. So this is the class, this is F1, F2, F3, F4. Do you see that? So that's our data set, you know, and then we can use it. So to process data, one important library in Python is something called Numpy. All right, so Numpy, let's say once the data is in matrix data, which is a variable, it can be processed as a Numpy array matrix. So what does that mean? It means that, you know, if you've used Python before, you're familiar with using lists, right? So you create a list of values, you know, L, and it's comma separated, and you have, it's basically a data structure, like an array. But you still have to process it like an array, so you'll do for I in range, you know, 5 or something, and then you L I, right? And you start processing things that way, and that's the way you write your code. But that's not a very efficient way of processing things, right? Because you want to really take advantage of more efficient methods. So what Numpy does is that it allows you to introduce linear algebra techniques into Python, so that these algorithms have been optimized in Numpy to be very efficient. They are much faster. So writing code like this is going to be considerably slower than writing code in Numpy format, right? Because you have this idea, so anyone that has used MATLAB, for instance, knows that MATLAB is a matrix-oriented environment. So this means that this is no longer just an array, which is what I just said, but instead it is more of a vector or a matrix as in linear algebra. So many operations are now simplified, like extracting certain columns or row through, and this is usually referred to as slicing, but also doing operations now can be more efficient. So here's some additional code now on how to get the data. So as you can see, you have create a variable numpy, fnumpy. You read the data set from some CSV. Right? Then you then use numpy load txt, for instance, from a text file, and you give it this object fnumpy. You skip row 1 so that you don't include the header. So that means like if you have f1 literally legitimately in there, f3 and c1, you basically skip this and you just go to the data itself in your matrix. Then here you can see if you want to get, you can do little tricks like if you want to know the length, the number of, what is this? The number of columns, right? So you slice from the matrix, you have your matrix, you just grab index 0. So you grab that index, right? You guys see that? And then you say all columns, so you look at all of these. And now you can count them, and that gives you the length. So that basically, that little trick allows you to know the number of features, including the class, in your data set. So we can print here then something like print A. All right, here are other examples of slicing. This is very similar to the other one. From the matrix, we grab all rows and these columns. You can see that here as well. Another way of doing it is all rows and all columns from the beginning until 18. See that? Because we provide after the comma, you have colon 18. So there's nothing there, so that just indicates from beginning until 18. And that's the range that we specify. All right? And then finally, if let's say this assumes that maybe this is feature 19, and that's actually the class. So that's actually the class. Right? And so this class then, we just want that. So basically we tell it all rows and column 19. So this results, y is going to result in one vector that is a vector going down like that, right? With just one column 0 for the classes. Make sense? Any questions? No? All right. All right, so let's keep going. Now we can calculate the dimensions of the matrix, as in that one, which gives you the number of columns or the number of features plus the class, which is what I had indicated before. The following code example shows how data can be read with another method called numpy load.txt and slice from the matrix test data into two matrices, x test and y test. So this is also important because remember that whenever you're evaluating your models, you'll have a data set, let's say from 1 to 100,000, but you need to use this data to train the model, and then you need to, once you've created the model, you want to see how good it is, right? So dividing the matrix into two parts, train and test, allows you to do that, right? So now you only train on this data set, that part of the data set, and you leave this out as a separate data set for testing, all right? Now usually this will be like 70% of the data, or 70 to 80%, and this can be from 20% to 30%. You see that? And so those are kind of the numbers. Notice that x test has all rows. So now let's look at the code, and then we'll come back to the text. So you can see the same thing. We create a file, we open it. This is our file in CSV format. Then we load it, f test, which is that one, skip rows 1, and then once again we, in data here, test data, we take from 0 to 18, that's the x, and then just the column 19 is the y. All right. So notice that x test has all rows from test data and columns 0 to 18, whereas the y test matrix has the same number of rows but only one column. Any questions? Any questions or anything you find confusing or no? Is this helping me writing on the slides? It helps? Yeah? Okay, another topic is feature scaling. So I should call this feature reduction. Feature reduction topic, right? And feature scaling is very important to achieve good results in classification tasks. For example, in principal component analysis, PCA, which is a feature reduction technique, feature scaling is very important. So that means if you don't do it, then your results will not be as good. The purpose of PCA is to project data to a vector that captures the most variability in the data, right? And so you want to make sure that everything is scaled correctly. So the classic example of feature scaling is, imagine that you have 3 data points, F1, F2, F3, right? So you have age, weight, and then income, right? Income for a person. So think about it. If we plot this, because this is really like that, right? So it's 3-dimensional vector space, right? Then we would say age goes from what? 0 to 100 probably. So that's age. And then weight goes from, let's say, also 0 to 400 pounds, right? But income goes from what? How much did Jeff Bezos make last year, right? Or, whoever's making a lot of money, so $1 billion. See, there isn't even enough room for this axis, right? It's so big. So if we rescale this, this might turn up like that. Do you see that? And so this feature here is too long in comparison to the other ones. Do you guys see that? And that's what scaling is. Scaling is, I'm going to scale all of these to be from 0 to 1. Right? Because it's going to be in relation to 400, or in relation to 100, and in relation to 1 billion. Right? And so that allows you to create this and make it into something that's proportional. Right? So that's what feature scaling is. So if the features are not scaled properly, one feature could dominate over the others and therefore be considered as the most variable feature. So usually the recommendation from a practical point of view is that feature scaling should be done. So feature scaling here should be done, right, for all your tasks before you do any machine learning. So here we have a little bit more. So with feature scaling, features with real valued numbers from any range can be mapped to other ranges, such as 0 to 1 or -1 to 1. This is performed for all features so that no one feature will dominate in the model. And other classifiers and deep learning models are also very susceptible to feature scaling. So it's definitely something that you want to do.